Welcome to this lecture on good and bad optimization models, insight from Rockafellians. Imagine that we have an optimization model, just abstractly represented as minimizing some function phi of x. Is it good or bad? Well, that can mean many different things. Maybe we're thinking about this is a well-posed problem. Does it have a solution? Is it computationally attractive in any particular fashion? Is it better than an alternative? These are the things that we like to look into when we formulate and analyzing an optimization model. The tool that we're going to use to analyze optimization model is going to call a Rockafellian. This is a concept that has a long history, goes back 60, 70 years, but has never earlier been spoken about under the name Rockafellian. In fact, as you can imagine, this concept is due to Terry Rockefeller, which himself, he called it a bifunction. But since we like the word bifunction in other contexts as well, we have settled to start using the word Rockafellian. So what is a Rockafellian? Well, say we have a problem of minimizing some phi. A Rockafellian for such a problem is a function in two variables. M-dimensional vector that I'm going to call u, and then the actual decision variables, n-dimensional decision vector that I'm going to call x. A Rockafellian then is this function f when it satisfies the property that if I put in a particular u bar that I'm going to call an anchor, then I reproduce the actual objective function. But of course, there are many other possible u's. So really, the Rockafellian really defines a whole family of functions of x. Let's try to make this a little bit more concrete. So we are in a modeling situation. We are addressing a real-world application maybe. And in that process, we come up with an objective function phi. I'm going to think about that phi as also being allowed to have the value infinity. So if phi is some sort of cost, a cost of infinity is very bad. And in fact, I'm going to use such infinity to model infeasibility. So although in the past here, you saw just an objective function, that is not, you shouldn't take that as a sign that I'm only worried about unconstrained optimization. No, not at all. But from time to time, I'm going to represent a general problem that might be constrained by just a single objective function where I set infinity to every value, to every x that is infeasible. Okay, with that convention, when you see that R bar, the real line with a bar on top, it just means that I have extended the real line to include infinity and plus infinity to allow us to model things in this fashion. Of course, later on, we want to get into many more details. And you can see that, of course, we need to bring out problem structure as well, but that will come a little bit later. Okay, so the actual problem is then to minimize some phi. There might be constraints built in there. So a Rockafellian now, what does that do? A Rockafellian would depend on two variables, a u and an x. And it actually defines a whole family of problems. For each u, you have an optimization problem in x. Of course, there's one particular u, that anchor that I talked about, u bar. If I use that particular u, I just recover the actual problem. But Rockafellian defines a whole lot of other problems as well, a whole family of problems. And looking at this whole family of problems, that's going to provide us a lot more insight about our problem and going to be able to allow us to make an assessment if your model is good or bad and many other things. So the things we're going to go through is various types of assessment of optimization models. We're going to get to that later on, even get into optimality conditions, computational strategies, and even see how Rockafellians define dual problems. But first, let's talk about model formulation. How can we write down an optimization model in a productive way that is easy to analyze? Of course, one could write an optimization model as some sort of minimize some objective functions subject to a list of constraints. I would like to bring out a bit more detail, and I think that's very important, especially in a non-convex setting, where we have to really take advantage of the structure of the problem that we might have. So to try to bring that forward, we're going to make a distinction between a basic feasible set I'm going to call X is a really hard constraint that we're not going to deviate from. This has to be satisfied. And then we're going to have a primary quantity of interest. We would like to somehow minimize that. But that's not the only thing we're worried about. We're also worried about M, secondary quantities of interest. We also like to see them having certain values, and what values are good for us is going to be governed by these monitoring functions. With these names, we're going to end up with a problem in composite form. We're going to see many examples of this, but basically we have a basic feasible set. I'm not going to deviate from that. We have some sort of cost maybe. And then there's some additional terms added on. Maybe these are penalties, regularization, maybe it's hard constraints as well. And we want to see how many situations can be cast in this form, and have this structure is useful in our analysis. Here's our first example. So we talked about the actual problem of this form. Let's look at a particular example of what these pieces could mean. For instance, F naught could be some sort of initial cost that we are facing. We want to minimize it in some fashion. But then we also face subsequent costs. In fact, M of them, because the costs are unknown. So maybe this is some sort of secondary cost that we are facing. But we don't know exactly what it is, because maybe the future is unknown. The only thing we know that there are these M possibilities, each occurring with a probability pi. So since we have now several possible costs in the future, it would be natural to look at the expected cost. And the expected cost can be captured by a particular monitoring function, which is a weighted average now, weighted with these probabilities of these different FIs. So then this term that we have been seeing, H composed with F, is nothing but the expected cost across these scenarios. So this actual problem that we're talking about could very well be a two-stage stochastic optimization problem, for instance. We can also model hard constraints within this framework. Imagine that these secondary quantities of interest, these FIs, must actually equal to zero. It's a hard constraint. Well, we can capture that by adopting a monetary function that is given as the indicator of zero. That I-looking letter is actually the Greek letter iota, is my notation for the indicator function, and the indicator function is zero if you are within a particular set, and infinity otherwise. So if I have such a monetary function, really I'm forcing, if you're looking at this term up here, I'm really forcing f of x to be equal to zero. Otherwise, I'm going to get an infinity penalty. So I'll probably shy away from that and force myself to pick x's, which has f of x equal to zero. So certainly hard constraints, equalities, inequalities can be captured by such monitoring functions. Here's an example from multi-objective optimization. Maybe imagine that we don't have that primary quantity of interest, but we have some I equal 1 through m. We would like to all minimize them, but of course, the challenge with multi-objective optimization is that we cannot bring all of them down at the same time. But maybe we have a goal for each one of them, called the goal tau I, and we like to get as far down to tau as possible. One possibility to achieve that is by adopting this monitoring function, where this theta I think was some sort of weight or a penalty. In fact, is a per unit shortfall penalty. Because see, if my Fi is strictly above tau I will then get a penalty per unit of theta. If Fi gets down to tau, then I get 0 penalty. So I will strive to get as close as possible to my goals. So this is also captured by this composite form. The problems have been a bit general, I guess. Let's make it a little bit more concrete in a particular application, one that I'm interested here at the Naval Postgraduate School. The US Navy operates in many places around the world. And actually, different battle groups are able to stay at sea for a remarkably long period of time. They don't need to go into harbor to refuel and this and that. And the reason that that is possible is that they resupply at sea using a fleet of transport vessels, like the one in the middle here, then meets the fleet somewhere and refuel them and provide them other things that they need. And these transport vessels then think about some sort of a shuttle that go from the harbors out to the fleet and then maybe to another battle group and then go back to the harbor in that fashion. As you can imagine, this is a major logistical challenge. It is a challenge that's been addressed by an optimization model. Paper starting with Brown and Carlisle, two of my colleagues in 2008, laid the groundwork for this, and this has been expanded since. This is an optimization model that is in use daily within the US Navy to determine how these transport vessels should be used. Okay, so I'm not going to go through the model in detail, but let's talk about the essence of it. And the model is centered around 4 commodities. Those 4 commodities are jet fuel. Let's imagine a carrier would need jet fuel for its aircrafts, but there's also bunker oil. And then there is a food and dry store that, of course, needs to be supplied. And then there's munition. So these are the 4 commodities that one would like to maintain really a good inventory of. So let's use the following notation that FBCD is the inventory of commodity C on day D for battle group B. And of course, all of that will depend on what decision we are making. Let's just call that decision X. And what is a decision? Was a long vector X. And it is really how we are driving these shuttle ships from the various ports. Where do they stop? What do they offload? Where do they go next? And all those things that, of course, an optimizer will have to determine to find a good plan. But we did not get into the details. One would imagine such an optimization model to have the following hard constraint, that the inventory should be greater than or equal to 0. That seems to be a no-brainer. Certainly we like to have our inventory greater than or equal to 0. No discussion about that. But that is actually not the case in this model. Transport ships are only encouraged to resupply. They are not forced to it. And they are encouraged through a system of penalties and rewards. And that is modeled using monitoring functions in the fashion that we've been talking about. In fact, the monitoring function is a sum of monitoring functions for the various terms. Each one of them is illustrated on the bottom here. And imagine here on the first axis that we talk about inventory on a particular day or a particular commodity for a particular battle group and say that is 100%. So then you're out here at 1. And then you see that the monetary function is slightly negative. That means that you get a little bit of a reward for being in such a state. The situation gets less rosy as we move to the left. In particular, as we go below 40% inventory for this commodity, we start accumulating a penalty. That penalty gets more severe as the inventory falls below 20%. And in fact, the inventory can fall below 0, but then there's a big penalty. So using a penalty system like this, the transport vessels are encouraged to go and resupply. And actually that results in a very good model. And what we want to see in this talk is why such a penalty system actually is a really good idea from a practical modeling point of view. And that insight will come from our Rockafellian. Okay, so let's get into a little bit more formal analysis about optimization models. Talk about an asymptotic analysis and how that can be done, including in the context of that Navy problem. So let's think a little bit about a Rockafellian. A Rockafellian is really just a way of quantifying what happens if there's a parameter that is being changed inside our model. So if there's one or more parameter that I'm really worried about, maybe because it's unknown, maybe because it's difficult to pin down for some reason, that might be a parameter that's going to help me to select which Rockafellian that I'm going to be using. For instance, in that composite setting, we remember we had a primary quantity of interest, we have a basic feasible set here just indicator function, and then there was this h of f. But now I'm tagging along a u, meaning that I'm perturbing these secondary quantities of interest, and that might become my Rockafellian. So there will be a case where the anchor is at 0, because if I set u equal to 0, I'm back at the good old problem that I started out with in composite form. But by changing a u a little bit, we can explore what is the effect of changes to the secondary quantities. And among the things that we can learn from such a Rockafellian would be, for instance, the classical right-hand side perturbation that we know from sensitivity analysis in linear programs, in convex analysis, and things like that. So what would you like from a particular optimization model? Well, maybe one thing that is fundamental, and maybe fundamental in any mathematical model, is if you change a parameter a little bit, the solution shouldn't change dramatically. In our context, we are interested in minimizers and minima. So to formulate that principle here, we really would like to have a model where if we change u a little bit away from the anchor, the minimizers and minima should not change too much compared to the values that we have at the anchor. That will be a feature of a good model. What would be an example of a bad model? Well, imagine here a simple example where there's an objective function x squared plus 1, and there's some sort of quadratic constraint. Imagine that we are adopting the following Rockafellian, where, okay, we have the objective function, and then I'm writing the constraint using an indicator. And what I'm doing is I'm adding plus u here, so it looks like the anchor is 1. So if u is equal to 1, I'm back to the actual problem. But what I'm asking myself, what is the effect of changing u away from 1? Well, in the notation of the minimum value function, so the minimum value function is p of u. Just, let's minimize the Rockafellian in respect of x, we get the minimum value function. And try to plot that. In this case, it's easy to work out. So here is a plot of the minimum value function as a function of u. And we are particularly interested in what's happening at the anchor, which was 1. And here we see something disturbing. If you are to the left of 1, we see the minimum value indeed is a continuous function. But as we pass 1, the minimum value function becomes infinity. And you can probably maybe see it from the numbers here that the problem is becoming infeasible. But for u greater than 1, the problem is infeasible, and I interpret that as a minimum value of infinity. So indeed, there's a dramatic effect for changing u around 1. And I think that's bad news, because if I was a little bit uncertain about the exact value of u, I can be greatly misled if I make the wrong choice about u. So in that sense, I think this is a bad model. How can we make an assessment of this kind more general, where the numbers are not as simple as in that example? And the key thing to look at are the epigraphs. So imagine that you have an objective function phi. What is the epigraph of phi? Well, it's simply just the points on the graph and above. For instance, in this so-called bad model that we looked at just for a moment ago, we had a Rockafellian that looked like this. Let's look at particular values for u. For instance, I think this is where u is equal to 0. And what is the epigraph now? Well, it looks something like that. And if I look at u equal to 3/4, then the epigraph of the Rockafellian looks like this. And I guess in the last picture, u has been selected 1, equal to the anchor. And then the epigraph is actually just a sliver, a straight line, straight up. But it seems like this epigraph has some sort of convergent property. And that is indeed going to be a key thing for us to examine. And that gets us to the concept of epiconvergence. Let's denote the smallest distance from a point to a set as this dist. And let's index sequences with this Greek letter nu. Okay, so it's going to see some usages in index of a sequence. Okay, so here's the definition of epiconvergence. If you have some bunch of functions, phi nu, they epiconverge to phi, and sometimes I just write arrow E to indicate epiconvergence. That happens by definition if the epigraph of the limiting guy is a closed set, and then the point to set distance from any point z to the epigraph of these approximating guys converges to the point to set distance for the actual. So in this picture, I guess it looks like I picked a z here, and I look at the distance over to the epigraph, and I see how that is evolving as I go from one picture to another one. And if that distance somehow converges, I will have epiconvergence. So epiconvergence is really just about the epigraphs converging in the most natural way. What are the consequences of epiconvergence? So imagine that we have some functions, phi nu epiconverging to some phi. Then we really have a lot of what we want from an optimizer's point of view. In particular, minimizers can only converge to the minimizer of the limiting problem. We have things about level sets being convergent, and even minimum values are convergent. So how can we use that in the context of Rockafellians? And in particular, think about stability. So we have our actual problem, and we have settled on a Rockafellian. So now maybe we are worried about how much does the minimum value change? Like typical sensitivity analysis, how much does the minimum value change as we move away from the anchor? And we can then have the following fact. If my u converges to the anchor and I have epiconvergence, then these minimum values will actually converge, and the minimizers will also converge. So this means that if I worried about what's the effect of making some changes in U away from the anchor, the property to look at will be epiconvergence, and I will settle the question if my model is good or bad in this sense. If I have epiconvergence, my model is good. If I don't have epiconvergence, in some sense, my model is unstable. We can go to various examples to see how all of this will come together, for instance, in a regularized problem. Imagine that the actual problem of interest is to minimize some objective function, which consists of a phi naught, maybe some sort of loss or something. And then there's a regularization term that has a weight that is theta. And maybe we are worried about what is the right theta to use in a particular application. That might drive us to define a Rockafellian, where the key thing that is varying in the Rockafellian is the theta. So theta becomes a function of U. And we wonder what happened when that theta converges towards some sort of limiting the quantity. Maybe the limiting quantity is 0, corresponding to the actual problem, or some other limiting quantity that we would like to look at. It turns out, under very mild continuity assumptions and boundedness assumptions, this model is stable. We have epiconvergence, and indeed, this will be a good model in my book. What about risk-averse decision-making? As you know, many times in finance and engineering, we would like to minimize some sort of super quanta risk, or what's also called conditional value at risk or average value at risk minimization. That gets us into this problem here, where P size the probability of a particular scenario, and the quantity that we are worried about is this G. Maybe this is the value or the cost we are facing next year is unknown, but we can influence it by making a good decision X. But what is often a bit tricky to settle on is this alpha. This is the risk averseness parameter. And you might remember if alpha is close to 0, this corresponds to risk neutral. If alpha grows, become more risk averse. And how you settle this can be difficult. It has to do with preferences and things like that. So maybe we will look at what is the sensitivity or the stability of the model relative to alpha. Well, that will trick us into defining our Rockafellian of this form, where U, as we've been denoting it so far, is actually alpha in this case. So alpha is playing the role of U. And we wonder what type of stability properties do we have in this case as well, under mild assumption about continuity and boundedness. Actually, we will see that this model is stable. So actually it's not that critical to get the alpha right, because minimizers and minima will not change too much if we deviate from any particular alpha. So in my book, this is a good optimization model. We can, of course, proceed in much more general settings as well. Imagine the full composite form. One possibility we can look at a perturbation where we change the second order, quantities of interest, the secondary quantities of interest. We talked about that a little bit before. Again, we can get a stable model, but here things are a little bit more delicate. One way to get it is to have H being real valued and continuous. That is indeed the case in goal optimization, and indeed the case in the Naval resupply problem. So by looking at through this angle, we actually can get a reasonable confirmation that, for instance, the Naval resupply problem is a good one. It's a good model that's been chosen there because of these penalty systems are incorporated, and they are real value continuous penalties. So actually the model is stable, as we are perturbing the secondary quantities of interest. And in the Navy problem, what are the secondary quantities of interest? They're actually inventory levels, which of course directly related to the consumption rates. And consumption rates are the ones that may be the main thing that is a bit uncertain in such a model. But because they're using a penalty system, small changes to such consumption rate actually will not change the decision very much. And we can see that through a Rockafellian of this kind. In contrast, if this has been implemented as hard constraints, that we need to have inventory level greater or equal to 0, or whatever threshold you like to put down, then this will have been a bad model. And we've already seen that how a hard constraint produced a bad model. And this would have been problematic and had produced potentially very erratic solutions, very much dependent on if you got the consumption rate right or not. Okay, we can continue and talk about this also in the context, for instance, in penalty methods. Again, we can look at the Rockafellian and see that, yeah, actually, such penalty methods are also pretty stable, good in my book. Okay, let's move on and let's do a little bit of background just to be able to get into the subsequent issues more seriously. I'm going to give a little bit of background, a really fast one, about normal, cones, and subgradients. Very fundamental quantities, and just hope to expose some of these concepts. And of course, one will have to get into them in more detail. So what's a normal cone or a normal vector? Well, maybe the picture on the bottom is most helpful. Imagine that you have a set C here. Maybe it's a feasible set. And you might know what the normal vector is. Well, it's a vector that looks like that, points outwards. And the key thing is that it forms more than 90 degrees with any vector pointing inside the feasible region, and that forms a normal vector at such a smooth boundary point. The situation is similar if you have a corner point like here, but now the normal cone actually widens normal vectors in many different directions because there are many ways to get more than 90 degrees compared to a point inside here. So it is a bit of a more wider normal cone, but that's fine. A small complication arises if you're on an inward cusp. Imagine this top of this heart shape that we have here on the right at this point here. Here it's impossible to find a vector that points more than 90 degrees away from every vector pointing inside the shape, inside the set C. So because of that, what we call the regular normal vector is actually just 0. Okay. So that's where we like to supplement this regular normal vector with some limiting quantities. Basically, what are the arrows that you get by looking at neighboring points as those neighboring points get closer and closer. So at such an inward cusp, in this case, the normal vector are these two black solid arrows. Those are the normal vectors, and they form the normal cone. So that will be a more robust way of thinking about it. And we'll need to talk about this in much more length, of course, but I think the important takeaway here is that while traditionally maybe normal cones have been taught in the context of convex analysis, but here we are going to have it defined for any set, convex, non-convex, perfectly fine. And actually, normal cones are going to help us to define subgradients as well. If we have a function phi, we can draw the epigraph of it, and that's what I have here. So now, what is a subgradient? Well, it turns out the subgradients for this function phi are given by the normal vectors of the epigraph. So if you stand, for instance, at a point here, I think you know where this is a smooth point, derivative. The slope of the curve looks like roughly 1, doesn't it? So maybe this is a situation where the derivative is equal to 1. How would that come out here? Well, one will draw the normal vector at this point, and that's this black arrow. And then, as indicated by this definition here, one will go 1 unit down and see how far over to the right one will go. And that is the gradient in this case, or the derivative in this case. More generally, it would be the subgradient. So this applies even at the point of non-smoothness, as we see down here. But there, of course, now there's a whole set of subgradients. And that's something that you would have known from convex analysis. But this will apply even at non-convex point, like the inward cusps here and things like that. So the main takeaway from this is that we can define subgradients for any function, convex, non-convex, doesn't matter. And these are sometimes called more the covariant subgradients, but I'm just going to use the word subgradients because these really are the most important kind. Just a few things about calculations. The good news about subgradients defined in this particular way is that they have calculus rules, so we actually can compute them. In particular, if you're in a smooth case, subgradients, just a good old gradient. If you have a sum of a phi 1 and a phi 2, what's the subgradient of a sum? Well, if one is smooth and one is non-smooth, we can just add it together like that. And here's a particular case. Imagine that you have the indicator function of a set x. Well, what is the subgradient of an indicator function? Well, it turns out to be the normal cone. Again, convexity is not required, just could be any set x. Okay, what is all this is getting us? Well, it gets us the basic optimality condition that can be traced back to Fermat. And what this is saying is that you have a local minimizer of a function phi, then 0 must be in the subgradient. That is the basic optimality condition. Of course, derivative equal to 0 from calculus would just be a special case. Okay, I need to get into a small thing, which is an important one. It has to do with constraint qualifications and things like that. And I'm going to explain that in the context of so-called horizon subgradients. Just want to remind you quickly that a function phi is so-called lower semi-continuous, or LSC, if the epigraph is closed. So everything is thought through the epigraphs. Okay. With that, what is a horizon subgradient? Well, it is again defined in terms of normal cone of the epigraph. So I'm back to the picture that I left you with earlier. There's something special happening over here. And that is that the normal cone points straight to the left. That is a case where we don't have subgradients. But we have some sort of information at this point still in terms of the normal cone at that point. And those directions that points horizontally like that, those are examples of horizon subgradients. We don't have any here. We don't have any here. But over here, again, we have horizontal normal vectors. And in that case, we'll have horizon subgradients. And these will help us to characterize constraint qualifications. And then my notation for all of that is this partial symbol with an infinity superscript. So when you see that, just keep in mind that I'm talking about horizon subgradients. And there will be calculus rules for computing those things, but I'm not going to get into all the details. Okay, so how is all of this in the context of the naval resupply problem? Well, you might remember that in that case, the monetary function was a maximum of affine function. I guess that's illustrated in the picture here. We would then need to compute subgradients here. Well, whenever there's a kink, we're going to get multiple subgradients as indicated here, but one can compute it. The main thing to take away from this is that the way we're setting up subgradients is in a fashion that can be computed. That is in the convex and in the non-convex cases, a rich set of calculus rules that can be used to make such computations. So subgradients are really something that we can work with. Okay, with that little bit of background, let's get into a quantitative analysis now. Imagine that we're talking about a particular function f, probably Rockafellian, and imagine that we have the minimum value function. And we are wondering how much does the minimum value change as I vary u, classical sensitivity analysis, but now expressed in terms of a Rockafellian. Well, it turns out that the subgradients of the minimum value function can be characterized, at least in parts, by the subgradients of the Rockafellian. So if you wonder, how much does my problem change? How much does the minimum value change as I change u, as I move away from an anchor? The thing to compute are the subgradients of the Rockafellian. We can look at this in a concrete setting. I was playing with this model a little bit earlier. So we'll see how that comes out in this case. We had a particular Rockafellian. Well, let's change the anchor. I guess I used to have anchor at 1. Let's make the anchor 0 now. And in that case, when I actually can compute the minimum value function, we can compute the subgradients. It turns out to just be 2. So the picture we have in mind is that if we now center here the origin, it turns out that we get this sensitivity estimate. And of course, we have convexity here, so we can do a little bit better. But you can see how the subgradients provide an estimate of how the minimum value function change as u changes. This can be much elaborated on as we move into a general composite problem. This is a busy slide. We provide all the details in that composite case. I'm not going to go through all of that, but under pretty general assumption about all these things, we can actually determine the subgradient of the minimal value function. So we can make a quantitative assessment of our model. Does the minimum value change a lot? Or is it pretty stable as we change u, and we can learn about that by looking at these subgradients. As a concrete example from inventory management, imagine that we have the classical EOQ model, economic order quantity model, where we have a certain number of units sold per year. We have an order quantity that we need to determine and optimize. And we have a certain inventory cost. And what we know then that inventory cost is going to be alpha x divided by 2 in my notation. But imagine we have an aspiration sigma for that in sort of a goal optimization setting. We hope to bring that cost down to sigma. I'm not sure if we're able to do it, but I would like to. And the same with the ordering cost. I have an aspiration level or a goal of tau. I will hope to get it down there, but I'm not sure. So I can formulate a goal optimization model of the way we talked about. Here it is. In that particular case, I guess this will be a particular monitoring function. We talked about the details earlier. So now imagine I worried about these aspiration levels, tau and sigma. How close can I get to them? But I wonder, where should I set my goals? They're really important. So I'm going to look at perturbation with respect to those goals. So that will correspond to perturbations of this secondary quantity of interest in my terminology. And one can develop exactly the subgradients in that case. And here's a characterization of it. And of course, if we simplify a little bit, for instance, if we set that the goals are 0 cost, and we try to get down to that, we can see that actually the gradient of the minimum value function will be this half-half. So we can carry out the full sensitivity analysis and get concrete values for these quantities that we have seen here in rather great generality. Okay, let's move on and talk a little bit about optimization, optimality conditions. Okay. It turns out Rockafellians can also be dealt with or derived, or rather optimality conditions can be derived from optimality conditions. Okay, so here is an optimality condition. Let's go back to Terry Rockefeller. And it's an optimality condition, not surprisingly, defined in terms of a Rockafellian. Basically, it says that imagine that you have the problem minimizing pi. Then it turns out that if you have a minimizer of that problem, then as a necessary optimality condition, you must have a multiplier y in a generalized sense, such that y0 is in the subgradients of the Rockafellian. So every Rockafellian will give you an optimality condition of this kind. And this is even sufficient in the convex case, as we're familiar with, and is necessary in the general case. We can specialize this in various ways. So this is really a blueprint for how we can construct optimality conditions in various ways for various problems. For instance, in a composite problem that we'll be talking quite a few times, it is the problem here. Imagine you have a local minimizer of that problem. Then it turns out you must have a multiplier y such that something is true. That's an optimality condition that we can derive from the previous slide. How do we do that? We start with a Rockafellian that looks like this, which looks at a particular u of this form and the anchor of 0. If you do that and compute the subgradients, you will obtain the optimality conditions as we just saw. And in fact, you can derive the Karush-Kuhn-Tucker condition in this exact way. And you will also get the Magasari and Fromowich constraint qualification by looking at the horizon subgradients. Okay, let's move in towards some computation towards the end. Imagine that we have the actual problem. And we have settled on some sort of Rockafellian, and the anchor is 0. Now, what we can do, we can construct a relaxation of the problem. Because if I allow myself not only to minimize over x, but also minimize over u, certainly that must be a relaxation. And that is regardless of which y, think about y as a vector of parameters, regardless of which y possibly equal to 0 that I might adopt in this model. And I can hope that maybe this relaxation is easier to solve. It's a bit of a lifting strategy. I've introduced some new variables, u, and by doing that, maybe the various aspects of our model that becomes easier. And you see every Rockafellian that I choose will produce such a relaxation. And this relaxation strategy is what we call Rockafellian relaxation. It's pretty clear that this leads to a lower bound through a relaxation. And how good is this lower bound? Well, that depends a little bit about what which y that you're selecting, and other things as well, as we will be talking about. Now, you know about the Lagrangian in classical nonlinear programming, going back to Lagrange. It turns out that we can broaden that view and have a Lagrangian coming from any Rockafellian. So if you start off with a Rockafellian, you can always define a Lagrangian L by minimizing the Rockafellian and subtract a linear form. That gets us a Lagrangian in a generalized sense. So what are concrete examples of that? Well, imagine if I have an objective function f naught, and have some hard inequalities here indicated by the indicator function, then if I compute the Lagrangian in the fashion that I just defined, I actually get the good old Lagrangian that you're familiar with from linear programming. And indeed, yes, those y's are the non-negative multipliers, often called the Lagrange multipliers, right? But this was just if I use a particular Rockafellian for a particular model. There are many other Rockafellians I could have chosen. So this really shows that there's a broad set of Lagrangian we can define within this framework. We can develop a Lagrangian also for the Rockafellian that we have often used in the context of composite optimization. In a composite setting, we had a problem looking like that, and we often like to look at perturbations of the kind, let's change up secondary quantities a little bit. That gave us a Rockafellian that we've been working on several times today. What is the Lagrangian corresponding to that? Well, here's a formula for it. And it turns out to be given in terms of the convex conjugate of H. Okay, let's discuss this in the context of constrained shortest path problem. So imagine you have a directed graph and you have some edge lengths, maybe that correspond to maybe time or something, how long it takes to traverse the edge. But then we also have some weights, maybe many, corresponding to each edge. Maybe that's fuel consumption along that edge or other secondary quantities that we are worried about. Maybe this is in the context of routing an aircraft from an origin to a destination. And the trouble here, I don't only want to minimize the travel time. Somebody's shooting at me, indicated by these red circles here. And I rather prefer not to be shot down, so I'll try to avoid flying near those things as much as possible, maybe within certain limitations on fuel and things like that. So that could be the context in which we want to solve a constrained shortest path problem. Well, how is Rockafellian relaxation coming out in this case? And in fact, in this case, it typically goes under the name Lagrangian relaxation. Okay, the actual problem can be formulated in this fashion, where x, what is x? That is a set that defines a path from the origin to destination nodes. And the one thing I would like to highlight here, see that x is actually involving binary restrictions. So there's nothing really needed, convexity or linearity or any of these properties are not needed in this context. We can carry out this type of relaxation in this case just as well. So if I define a Rockafellian now, where what I'm changing up is these weights or the secondary quantities of interest, and looking what happened to my model when I perturb those. So that gives me a Rockafellian. And from the Rockafellian, I will get a Lagrangian according to my definition. And in this case, the Lagrangian comes out like this. And what's special about this Lagrangian is that actually it corresponds for a fixed y to just our shortest path problem. So I can minimize this Lagrangian for a fixed y just using, say, Dijkstra's algorithm or something like that. So this was an example where Lagrangian relaxation, or if you like, Rockafellian relaxation, with a particular Rockafellian involving a right-hand side perturbation of some constraints, gave us a simpler problem than the original one. But it could be merit to solving that simpler problem as some sort of part of a solution strategy for solving the actual problem, which might be hard. All of this is also giving us paths to define dual problems. Imagine that we have an actual problem here, and we're defining a Rockafellian where the anchor is being placed at 0. We already defined a Lagrangian. So now let's imagine that we define a dual problem in the following fashion, where we're maximizing up psi, which is just the minimum of the Lagrangian with respect to x. So the dual problem in this setting is to maximize a choice of y, the minimum with respect to x of a Lagrangian. The Lagrangian stems from a Rockafellian. Depending on which Rockafellian you choose, you're going to get different Lagrangians and you're going to get different dual problems. The Lagrangian, from this point of view, actually plays somewhat of a secondary role. We could have defined this dual problem completely without a Lagrangian, because actually we can go directly here and say that the dual problem is to maximize this convex conjugate of Rockafellian. So the Rockafellian, through this conjugate operation, defines the dual problem. We didn't have to even bring the Lagrangian on board. Of course, Lagrangian has some nice things about it. It supports thinking around saddle points and things like that. But we could have defined dual problems without it. The key insight is that any Rockafellian provides a dual problem, these definitions. Towards the end here, just let's talk a little bit about the duality gap. And of course, that is important because how much information do we really have in that dual problem? If we compare the minimum of the actual problem, the max dual, we will hope it's 0, but sometimes it's positive. Of course, we know it's not automatic that we're going to have a 0 duality gap. And here's a small example that shows that certainly we may have an optimality gap even of infinity. But there are various sufficient conditions of strong duality and 0 optimality gap. For instance, if you start out with a Rockafellian that has a certain property, proper low convex, and the key thing to look is the minimum value function. If actually 0 is in the interior of the domain of that minimum value function, then you have strong duality. And maybe to help you to understand that, let's look at that minimum value function plot that we looked at a few times. So for instance, if I have an anchor here of 0, then I'm certainly inside the domain, in fact, in the interior of the domain of the minimum value function. So all is good. You will have strong duality. The trouble is if you move over here to 1 here, now you're on the boundary of the domain of the minimum value function. Because if you move a little bit to the right, the minimum value function becomes infinity. So in that case, there will be a situation where you may not, according to this theorem, have strong duality. Of course, we know that in convex analysis, Slater condition will suffice to get strong duality. And of course, Slater has to do with having a point where the constraints are satisfied strictly as indicated by this picture. So you have constraint function that looks like that and not like that, where indeed you don't have any interior of the feasible region. Well, it turns out, as you know, Slater condition is actually not necessary for strong duality. It's just sufficient together with convexity. And here's an example that demonstrates that. But the question is, how can one try to push the limit of it? And that is where the key thing is to think in terms of Rockafellian. And this is the last result. If we choose a good Rockafellian, we will going to get strong duality. And with that I mean, if I pick a Rockafellian that has this epigraphical convergence property, meaning that if I change up U a little bit, That is really the key property to get strong duality, because we know from the choice of Rockafellian, we'll get a dual problem. So if we just choose the Rockafellian right, we can get strong duality. And what is right? It is in the sense of epic convergence that we talked about before. There's some additional assumptions as well that you will have. But by going through this motion through a Rockafellian, you can actually, for any problem, being it convex or non-convex, you can construct a dual problem that has strong duality. Of course, the challenge is that dual problem really approachable and convenient for other reasons and things like that? That's of course on the table, but it's possible by thinking through a particular Rockafellian. One can then settle strong duality. And we can also use this theorem, for instance, to fill the holes that we had on the previous slide where Slater condition didn't hold, but we still have strong duality. And that can, for instance, that issue could be settled by looking at this theorem. Many of these things are elaborated on in much, much greater detail in our forthcoming book, an optimization primer that I wrote with Roger Wetz, that is forthcoming at the end of the year. Thank you very much for your attention.